Welcome everybody to the online seminar on numerical linear algebra. My name is Bart van der Rijken and I will be the chair of today's talk. The moderators for the questions are Valeria Simoncini on Zoom and Daniel Kresner on YouTube. Throughout the talk, you're welcome to post questions in the Q&A window of Zoom and the live chat in YouTube. We are very pleased to have Tammy Kolda as our speaker today. Tammy, if you're there, please enable your video and microphone and maybe share your presentation. Tammy is a distinguished member of the technical staff at Sandia National Labs and a fellow of SIAM and the ACM. She has been in Sandia since '99 and over the years has developed quite an impressive body of work on applying, in particular, tensor methods to all sorts of applications from industry and academia. I'm sure many of you are aware of her highly cited paper in Science Review on tensor decompositions. It is a paper I always recommend to people if they want to get started in this business of tensor methods. So thank you, Tammy, for that paper. Her talk of the day continues on this topic, computing low-rank decompositions using randomized linear algebra, which is another exciting topic in our field today. So Tammy, we are very much looking forward to your talk. Please go ahead.
Thank you. Thanks, Bart, and to all the organizers of the online session. And I just want to give a moment to acknowledge my co-author, another Brett. Brett Bader was the co-author of the Tensor survey paper, and now I get to work with Brett Larsen on this. So Brett, if you could just say a word so your screen will pop up.
Hi, everyone. Like Tammy said, I'm a student at Stanford, working with Tammy at Sandia. Thanks,
Brett. And I told Brett that he's the understudy. So if my internet goes down, he takes over. So thank you for having me to talk. Before I jump in, I'll just mention a few things. First of all, the slides are downloadable. And so I put the link at the top, tinyurl.com/E, N, L, A, -7-1, today's date. And then I just want to say that there's a lot going on in the world right now. And I just want to acknowledge that we have a global pandemic and a lot of people are being affected. Of course, we have this online seminar series as part of that, but a lot of people are being negatively affected through their health or through just added complications in their lives. So I just want to acknowledge that. And I also want to acknowledge the movement in the US for Black Lives Matter and addressing systemic racism. And I just want to encourage us all to do our best to be part of that. So now back to the math topic of the talk. So tensors come from many different applications, have become more and more ubiquitous. So there's been a lot of work early in the sort of tensor land in the field of chemometrics because tensors are a natural way to analyze fluorescence spectroscopy data. And so there we have a three-way array, which is arranged as emission level, excitation, and samples. So you can analyze multiple samples. With another student at Stanford, I looked at neuroscience data where we had a mouse running through a maze and there were multiple neurons being tracked over time and then multiple trials being run with the same mouse. In other work, we've also looked at Chicago crime data, which has been posted online. And you can analyze that as a tensor. You can look at the day of the crime. There's over 17 years of data, so quite a few days in the data set. The hour of the crime, and there is differences between daytime and nighttime, the location, and the type of crime. You can look at, there's many applications of machine learning. Here I mentioned higher order moments that are useful for Gaussian mixture models. You can also look at transportation data. There's New York City taxi cab data has been put online. I have a colleague who's looked at analyzing basketball data. You can look at cyber data, social networks, signal processing, trending co-occurrence on terms on Twitter, and much more. So there's many applications of tensors. Tensor decomposition can be used to find patterns in massive data sets. So it's a form of unsupervised learning, similar to things like principal component analysis or non-negative matrix factorization. So what does it do? So you're given some data tensor X, And in this talk, we're going to talk about a tensor of order d plus 1. So with the three-way tensor, d is 2. And what we're trying to identify is just a bunch of matrices. That's why we get to talk about it in a linear algebra setting. So we want d plus 1 factor matrices. The kth factor matrix is going to have nk rows. That's equal to the size of the kth mode of the tensor. And then all the factor matrices are the same number of columns R, which we'll say is the model rank. Technically, it's an upper bound on the model rank, but we'll just call it the model rank. So we take those factor matrices and then we put them together in a magical way to get out a tensor that's the same size as X. And so in some sense, the details of this magical way are mostly irrelevant for this talk. So I'll just mention it very briefly. So the model depends on these matrices. And then the ith element of the matrix, which is I is shorthand for I1 through ID plus 1, is to take rows of the factor matrices. So the I1 row here, the I2 row here, the ID plus 1 row here, multiply them together element-wise, so dot star in MATLAB, and then sum up that thing that you multiplied together. So it's kind of a funny way to go from these matrices to this model, but it corresponds to taking outer products, tensor outer products of the corresponding columns. All right, so let's just, I always like to start with some sort of motivating example, and Brett did Herculean, I can't say the word, efforts to get this model run. You'll see at the end how difficult this was, but we looked at a tensor from Reddit data. So Reddit, I have learned, is sort of a social discussion website and news website, and a subreddit is a discussion forum on a particular topic. And so this tensor we got from a formidable repository of sparse tensors, so frost.io, and built from comments that were posted in 2015. So you'll see that some of them are timely for 2015 and not for now. So they set up a three-way tensor, which is user by the form, the subreddit by the word. And the Reddit tensor is of size 8 million users, 200,000 subreddits, and 8 million words. It has 4.7 billion non-zeros, which sounds like a lot, but actually it's a very sparse tensor. So the density is 10 to the minus 8%. And it takes over 106 gigabytes to store this tensor. And the specific tensor we're working with is the log of 1 plus the count. So the IJK entry is a log of 1 plus the number of times user I used word J in subreddit K. And then we're going to compute a rank 25 decomposition. And so I mentioned that we want to do unsupervised learning on our data. So what would we get by analyzing this Reddit tensor? So we're going to compute a rank 25 model. This explains about 6% of the data. So if you want to explain more, use a higher rank model. Just to give you a sense for these 25 components, their relative weights, don't worry about the Y scale, but we're going to look at 25 components. And so the smallest is about, I don't know, 40% as big as the largest. So they're all significant. And you get to get those sort of like singular values. And then just to zoom in on the 6 component. So Reddit is a forum where people talk about everything. A lot of the components had curse words in them. So I tried to eliminate those. So I'm going to show you the 6th component, which is so far free of curse words. So what we're going to look at is there's 8 million users. I'm not going to show you a plot of the 8 million users. I'm going to show you just a plot of the strength of the top 1,000 users, just so you can get a relative scale of how it sort of falls off. And then we'll also look, and we'll zoom on this more in the next slide, at the top 25 largest absolute value of the 200,000 subreddits. And then those are color coded. And so really this one that's brown, which is Ask Reddit, gets almost all of the traffic at Reddit. So it's very dark brown, and the others are just shades of blue, but a lighter blue means it gets more activity than a darker blue. And then we'll also look at the top terms, and there you see more differentiation by color. Those are also color coded by overall frequency. And so the brown and red are very frequent, and then the blue is very infrequent. And so it's kind of interesting when the blue term pops up in the top words, because that's more unusual. So that really means that word is special for that component because it's overall not very frequent. All right, so let's zoom in on some of these components. So this component I started to show you, if you look at the words and the subreddits that are involved, it seems to be international news. So the top thing is world news. We also have Europe. And then the words, you'll notice some of the words look funny, like the top word is people with no E. And that's because the pre-processing used some sort of awkward version of stemming that sort of cuts off some ends of words. So country in blue is missing the ES. And then you also see world. So that's sort of international news. We also have a component on relationships, surprisingly free of dirty words, which is good. So we have relationships, relationship advice on the Reddits. And then on the top words, we see relationship, we see friend, we see someone, we see talk. So these are sort of things about relationships. We also have one on politics. So we see politics, this is from 2015. So we see Sanders for president. And we see in the top words, vote and state. And then we have another one that's on sports. So this seems to be a lot of different sports. So NBA, NFL, college basketball, and so on. And over in the top words, we see team and player and fan. We also have one, I learned a little bit about wrestling in this analysis. So squared circle, I guess, actually I didn't really look it up, but you know, it's a boxing ring is not a ring. It's actually a square. And so apparently they refer to this as the squared circle. And so you see top words as match and MMA, which I think is the name of some sort of wrestling league, and WWE, which I know is something with wrestling. And then we have soccer gets its own component. And soccer is big. Remember, this is based in the US, so it's really football for folks in Europe. You see FIFA, Liverpool, and you see player, team, league, goal, fan, and club under the terms. And then there's one for movies and TV. You see movie, film, characters. And then there's also a card game, which I learned is a computer card game from Brett called Hearthstone. And you see player and turn and deck and card. So this is the sort of analysis you can do with this. All right, so maybe you're now convinced that it allows you to sort of find things in your massive amounts of data. So how do we do this mathematically? So we're going to focus on the method CP alternating least squares. And so the basic idea is we're going to fix at each sort of sub iteration of the overall method, we're going to fix all but one of the factor matrices. So we might be in the middle and we've just solved for matrices A1 through AD. And then we want to solve for AD plus 1, and then we'll keep cycling through over and over again. Every time we are looking at everything fixed but one, we have a linear least squares problem. And that's the problem we're going to focus on making fast today. So everything's going to be about this linear least squares problem. So you can actually forget the tensor part and just focus on the least squares problem that we're going to look at. So what does this least squares problem look like? So you're going to have to forgive me for like the slightly weird letters because we're sort of tying together tensor stuff and matrix stuff. So our least squares problem is going to be ZB transpose minus X transpose. Z is a tall and skinny matrix that's size big N by R. B transpose is the unknown. It's size R by N. So it's a multiple right-hand side least squares problem. And X transpose is size big N by little n. Big N, I want you to think of as very big. So I have these dashed lines in the Z and the X transpose. And that's just to remind you that these are so tall, they didn't fit on the slide. So very, very tall matrices. And we can link this back to the tensor problem, although you don't actually have to for the rest of the talk to make sense. But this Z matrix has Khatri-Rao structure. We will pay attention to that. It's the Khatri-Rao product of the factor matrices A1 through AD. This means that capital N is the product of the first D sizes. So the product of N1 through ND. It cost big N times R just to form Z. So we are going to try and eliminate big N from our complexity. So that's sort of our goal. So we already have a problem just to form this matrix Z. B transpose actually just corresponds to the transpose of the D plus first factor matrix. That's the matrix we're trying to find. So that means N is just the last size, ND plus 1. And then X transpose is the D plus 1 unfolding of the matrix X turned on its side, or of the tensor X turned on its side. And the big thing to just remember is that it can be very sparse, and that's going to affect some of our choices. So this system, if you were to solve it, ignoring all structure, is big N, little n, r squared to solve. The KRP structure, it turns out, but you don't have to worry about why, that you can drop one of the r's. And then if it's also your x is sparse, you can actually reduce the cost to r times the number of non-zeros in x, which, you know, I think that's great. You could just stop there. And for most problems, that's actually a really big win, just to exploit the sparsity. But there's some problems like the Reddit tensor where the sparsity is so high that we really need to come up with something that's even lower than the number of non-zeros in x. And so that's like this Reddit tensor, and we'll see that we can actually even beat this complexity. All right, so but just think of this least squares problem. It doesn't really matter where it comes from, it just has this structure. And I will tell you what KRP is in a few slides. Just for simplicity, for most of the talk, I'm going to drop it to just a single right-hand side. It'll make it a little bit easier to tie it back to existing theory for randomized algorithms. So the single right-hand side problem, Z will be the same, but we'll just have an alpha and a nu. So we're solving for alpha, and nu is our right-hand side. All right, so I've been teasing about this Khatri-Rao product Z. So the Khatri-Rao product, sometimes we call it the column-wise Kronecker product. You could think of, you have these D factor matrices, and you're going to take their Khatri-Rao product. So every matrix has the same number of columns, R, but a different number of rows. And there's a one-to-one correspondence between each row in Z, so each little I in N, and a set of rows, a unique set of rows, one from each of the factor matrices, I1 through ID. We're going to take those corresponding rows, element-wise multiply them together, and that gives you the ith row of Z. So it's sort of maybe a different presentation than thinking of it as Kronecker products, but it works out the same way. So there's this complex formula. If you give me I1 through ID, I can give you the I. It doesn't matter exactly what this formula is, just know it's one-to-one. And then you multiply the corresponding rows of the factor matrices to get that row of the Z. So this is the structure that we care about. This structure doesn't just happen in tensors, it happens in many situations. So we're looking at problems that have Kronecker structure of the matrix. All right, so we're going to put together a lot of ingredients to make this random sampling work. I think there are 9 in all. So ingredient number 1 is just to use random sampling. So you have this tall, skinny matrix, tall and thin problem. We could just use a subset of the rows. So we'll let omega be a matrix that picks out a subset of the rows of Z. We'll pick out the corresponding rows of nu. And now we've reduced our complexity from big N to little s when omega is size s by big N. And so, you know, ideally that would just work. We're going to see it's not quite so easy. You have to be a little bit careful in how you pick those rows. And I'll just point to a couple of great surveys by Michael Mahoney and David Woodruff as references for a lot of these parts. So the question is, how can we make this sample so the solution of the sampled problem yields something close to the optimal residual of the original problem? And I'll formalize that in a couple slides. So first, just if you're randomly picking rows, we have to sort of pick things in a way that gives us the correct expectation. So it's an unbiased estimator. So just first thing is, just suppose I gave you a probability distribution on the rows of the linear system. So I'm picking them. And I'm not yet specifying how these are picked. We're going to get back to that later. But just suppose you have some probability distribution on picking rows. And then just say, for the sake of argument, we're just going to pick one row. How would I set my omega so that I get an unbiased estimator? So I'll pick there'll just be one sample. So omega is a big N by 1 matrix. And I guess here I'm sorry, it should be 1 by N, that's a typo. And then if I pick random index xi, then the xith entry is 1 over the probability of that entry, and everything else is 0. So this is going to pick out that one row, and it's just going to weight it by 1 over the probability that it was picked. And then you can convince yourself. So I have to assume that all my PIs are positive probability. So everything can be sampled. Then you can convince yourself that the expectation of this sampled thing, where I just sample one row, is equal to the true thing. And so I just look at the probability that each one was picked by the value if I pick that one. And then you could see that these PIs pull out of this squared norm. And then when you sum it up over all rows, you get back your original norm. So if I just pick one row and I did it over and over and over again in expectation, this works out to what we would expect. Now, we're not going to do just one. We're going to pick S. And I'm not yet telling you how S is specified. There are rules on that as well. But it's going to be similar. Now our omega will be S by capital N. And the jth row will be, if you pick element psi sub j, then the jth row will have zeros everywhere except for the jth entry, the psi jth entry, which will be 1 over S times the probability that you pick that element. And if you do that, each row has a single non-zero. And then as before, you can actually sort of as an exercise, convince yourself that the expectation works out. And so this is worth doing just to sort of get a handle on these types of methods. The first thing you have to do is make sure the expectation works out. If that's not happening, then you're sort of in a whole different class of methods that are biased. We really want to, at least I want to work with an unbiased method. All right, so now how do we connect all things? So we want to connect the probabilities that we're sampling, things called leverage scores, and the number of samples. So we're given our linear system. And we're going to pick our S entries. As I said before, we have a probability distribution, and we're going to set up the omega like we talked about in the last slide. And then we're going to solve this subsample problem. And so the solution, the alpha that solves that, we'll call alpha star with a tilde to say that it comes from this randomly sampled system. And then we're going to get this thing that says the following. For a given error epsilon and confidence 1 minus delta, if you take this alpha tilde star and you plug it back into the original system, that is in 1 plus order epsilon as good as the best solution to that original system. I just want to stress that we're plugging this back into the original system, not the subsampled system. So this is a 1 plus order epsilon good solution, at least 1 minus delta of the time. So with probability 1 minus delta. So this is saying with high probability, we're always getting a solution that's gives a residual that's in 1 plus order epsilon of the original, of the best possible solution. So to do that, what are the requirements? So the number of samples has to be order 1 over epsilon squared times log of R divided by delta. You can kind of ignore the delta times R times this magical thing, beta inverse. And beta inverse ties together our probabilities, P sub I, with these things called leverage scores, which I mentioned in the title. So I'll tell you what that is on the next slide. And then we get to pick the PI. So we don't have control over much in this process, except for picking these probabilities of sampling. And so we want beta is constrained to be between 0 and 1. We want to maximize beta because that will reduce the number of samples that we need. So the best beta we could pick would give us a beta equals to 1. That would happen if we set all the probabilities to be exactly equal to the leverage score of the ith probability was equal to the leverage score of the ith row divided by R, which just normalize it to sum to 1. That would be the ideal situation. So, but I'm about to tell you that's hard to do. So we won't do exactly that. So we'll try to do something that gets us as best as we can. So that's sort of how the number of samples and the sampling probabilities are tied together. So what are these leverage scores? So we have our matrix Z. Compute a leverage score, you let Q be any orthonormal basis of the column space of Z. You can get this via QR or the SVD. And then the leverage score of row I is the 2 norm of the ith row of Q, which is not intuitive to me, but that's what it is. And we define the coherence to be the maximum of all the leverage scores. That maximum has to be between R divided by N and 1. And the rough intuition is that rows with high leverage score are very important. So if we look at this matrix over to the left, If we have a row that has all zeros except for one non-zero, this row is critical for determining alpha 1. So if we don't pick that row, we're in trouble. And in fact, you can convince yourself that the leverage score of that row will be exactly 1. So this will be a matrix with high coherence. All right, so a lot of people will say that I just sample uniformly. So what if we do uniform sampling? So that means if we allow our samples be 1 over big N, so the beta will be R over N divided by the ith leverage score and what the minimum of that. So we care what our maximum leverage score is to minimize this, and that will affect our number of samples. So if our coherence was R over N, which means that all the rows have equal leverage, then if we plug that in, we'll get beta is 1, which is our best case. And the number of samples we need has no dependence on big N. It's just log R times R divided by epsilon squared. So that's great. If we have one of our leverage scores being 1, then our beta is R over N, which means that our samples is N times log R divided by epsilon squared. So it's worse. We need more samples than there are rows in the matrix. It's worse than just solving it directly. So clearly we don't want to do uniform sampling when we have a matrix that is coherent. So in case 2, we really want to customize our probability of sampling to be reflective of the leverage scores of the rows, but just computing those leverage scores would be NR squared. So that's our problem that we had to fix. As an aside, I'll mention that sometimes people transform the system by applying a matrix phi so that all of the leverage scores are approximately equal. So Michael Mahoney calls this uniformizing. I like that term, so I'll try to popularize it by using it here. So we want to uniformize all the leverage scores. One way you can do this reasonably efficiently in some cases is a fast Johnson-Lindenstrauss transform. And that would cost you, that's applying an FFT as well as a diagonal matrix, which has a random plus and minus 1 on the diagonal. And the cost of that iteration is R big N log N. So it's still too expensive for tensor problems. In previous work, we looked at how to do a Khatri-Rao product, a Kronecker product of FJLTs. And we can show that that is potentially, that works really well. The problem is that we can't use it in our problem where the right-hand side in the tensor problem corresponds to a sparse tensor, because this phi being an FFT will make our right-hand side go from sparse to dense. And so that's a problem where we can't use that method that already exists. So ever since we did this work, this previous work with Casey Battaglino and Gray Ballard, and also some analysis with Ruhi Jin and Rachel Ward, we knew that this wouldn't work in the sparse case. And so that's where Brett's job was to fix this. All right, so we can use the KRP structure to bound the leverage scores. There's an existing result that says that the leverage score of Z is less than or equal to the product of the leverage scores of all the factor matrices for the corresponding rows. So this is expensive to compute, but doing the leverage scores for the individual matrices is, relatively speaking, very cheap. And so this bound already existed. It was sort of invented simultaneously, although Simax is slower to publish, by 2 groups. And so now we can leverage that to make a sort of bound. So our probability of sampling, we're going to set it to be normalized 1 over RD is a normalizing factor of the product of the leverage scores of the rows corresponding to the ith row in Z. And then we can plug that into that existing theory that I mentioned before to get a bound on the number of samples. So the best case was R log R divided by epsilon squared. Because we're using a weaker bound, we get R to the D log R times divided by epsilon squared. But there's no dependence on big N. And so this turns out to be a nice bound. And then we still don't want to compute all these probabilities explicitly. So I'll sort of say how we get around that. But I'll take a moment and pause just to see we're about halfway through, or more than halfway through, if there are any questions.
I don't think there are any questions on Zoom or YouTube.
Great. I just know it's all crystal clear so far. All right, so so we now know what probabilities we want, but I still don't want to compute all big N of these probabilities. But it turns out you can implicitly sample according to P sub I without ever computing P sub I. And the way you do that is you're going to sample individually from each matrix. So you're going to sample the I1 row of A1 according to the leverage score for matrix A1. Similarly, you'll sample from matrix A2 according to its leverage scores and matrix AD according to its leverage scores. You'll put those together to get a sample in your sampled matrix. So you never compute big Z, you directly compute omega times big Z. And then you just have to weight that by the probability, but that probability is the product of the probabilities that you use to sample each of the individual rows. So that's what all this says here. So you never compute the big matrix Z. So you never compute the Khatri-Rao product. You never compute all the probabilities. You never even compute explicitly the sampling matrix omega. You're doing everything implicitly. And so the work is very low, and you can just have to compute the leverage scores for each factor matrix at a cost of R squared times the sum of the sizes of those factor matrices, the sums of the NKs, rather than their product, which is what would happen if you did Z. So this can result in a very big savings. All right, the next ingredient, and this can be used in any case where you're doing leverage-based sampling, it's not specific to the Khatri-Rao product, is to combine rows that have high sampling probability. So what we observed in some problems, so this is one example problem, is we had a problem that had the number of rows was order 10 to the 12th. We were taking 2 to the 17th samples, and we looked at how many of those samples had probability greater than 1 over S, so greater than 10 to the minus 6. And it turns out that 15,000 rows fell into that category, and the sum of their probabilities was 50%. This means that of our 2 to the 17th samples, half of them come from just repeatedly sampling from 15,000 rows, which means that in our final matrix, we actually get a lot of repeated rows. And there are other problems are similar. This is another problem that we ran into where 40% of the probability is concentrated in 10,000 rows. Here we have 25% of the probability concentrated in 7,000 rows. And just to show you these probabilities, this is just the top 15,000. You can see it's very concentrated. This is the top 10,000 and the top 7,000. A lot of the probability is concentrated in a few of the entries. And so after you do the sampling and before you move on to say your solve, like your QR, to solve your sampled least squares problem, it really helps to just go through and combine all the rows that were picked multiple times. And so we found that this could easily lead to somewhere between 2 and 20x speed up just on these examples I'm showing you here, and sometimes greater speed up. So that's one way to sort of tackle repeated rows. And so it's just sort of a best practice. And to the best of my knowledge, I haven't seen that suggested before. And so we just want to suggest this as a general tool if you're doing sampling, leverage scored sampling. Another thing that I think was maybe even more promising is to sample some rows deterministically and some randomly. So we're going to sort of split our sampled matrix, and some rows are going to come by just pulling out all the rows that have high probability and just putting those in there purposely, deterministically, so not randomly. And then we want to pick from the remaining rows randomly as usual. And so there has been some past work that suggested deterministic determination of your sampled matrix, but it only works if your probabilities have a nice drop off in terms of the power law. So that might not always happen. So this is a way that you kind of get deterministic if you need to pull some out explicitly, and the rest are sampled randomly. You have to readjust the sampling probabilities of these remaining ones to account for those that you removed. And then in our case, we actually can't even we can't directly compute all these sampling probabilities and then adjust them, because that would be big N work, but we can do something called rejection sampling. And so we kind of sample over and over again until we get something that was not in this set. We get the probability from the original thing, and then we can rescale it using the sum of the probabilities of the things we included deterministically. So I'll just refer you to the paper for more details on that. But this is a very nice thing that you could do, and it doesn't have to be specific to the tensor problem. Now, of course, how can I tell which has high probabilities? So our last big ingredient is to find all high probability rows without computing all the probabilities. And so remember, our probabilities that we're going to use for sampling are the product of these leverage scores. And so we want to find the set that all of the probabilities are above a threshold without computing all the values. And note that if everything has to sum up to 1. So if some are high, it means the rest must be small. So we're going to use that to our advantage. And so we can use a bounding procedure to eliminate most options and compute products of at most a few top leverage scores in each mode. And so we take the leverage scores and we sort them from greatest at the top to least at the bottom. And then we can say, well, look, if I take the top 2 probabilities from the other 2, and I sort this, at some point, we're going to hit a point where if I multiply this times the very top probabilities, it's going to be less than my threshold. So I'm just going to cut off. This is sort of like branch and bound. I don't have to look at these probabilities. Even matched with the top, they're not big enough. You do likewise for the second set, looking at the top from the first and third. And then for the last step, looking at the tops from the first and second. And now I only have to consider the products of these topmost ones to see if those are bigger than tau. And so this cuts off quite a bit of the testing that we'd have to do. And in fact, tau is something we just pick. So there are other ways that you can control this expense if you don't like just using a specific threshold. You could just say, I'm only going to look at the top few of each and limit it that way. All right, so now I'm going to just remind you that we're not just dealing with a single right-hand side, we're dealing with multiple right-hand sides. And so in particular, we need to think about how we go from this big sparse tensor X transpose, which took many gigabytes of storage, to a sampled version. And so I want to stress that we never form the unfolded matricized tensor at all. And then we actually have to pull out all the things have to do with the, say we sample row 7 here. We have to quickly be able to pull out all the non-zeros that have to do with row 7 in this particular unfolding. And so what we found is efficient is to pre-compute the linear indices, so these fiber indices, so that we can then search through and quickly pull things out. Even with that, it's still expensive to pull that out, but this is much faster. And so this results in a sparse right-hand side. And so we have to have ways to be somewhat clever about sampling that. All right, so now kind of giving you the math, let me just spend the last few minutes on the numerical results. So first of all, let's just look at this linear system and look at how the solution quality improves or not as you increase the number of samples. And so this is, in this example, we have N is 46 million rows, D is 2, I forgot to write that down. We have 10 columns and 183 right-hand sides. And so what I'm going to be showing you is we're going to look at the solution of the sum sample problem. And then we're going to also consider the solution to the full problem. So this one is small enough that we can actually compute the solution to the full problem in a not insane amount of time. And then I'm going to show you a graph that compares if I take this B star tilde and I plug it back into the original system, how much different is that residual compared to the best residual I could have gotten? And so that's what I'm plotting here. And so we have 2 different versions. One is we just take purely random samples based on the products of the leverage scores, as we showed you before. And then the blue is this hybrid where we deterministically include a subset of the scores. And so you can see that as the number of samples goes up to about 5 times 10 to the 5th, we get some very nice error bounds here. And a lot of times you think you can't even get a digit of accuracy. And I just want to show that here you can get several digits of accuracy with a reasonable number of samples. And then how many, for this deterministic one, how many samples are we including deterministically? So we increase the number of samples from 2 to the 7th to 2 to the 19th. And we set our threshold to be 1 over, or tau to be 1 over the number of samples. So that kind of is moving as we increase our number of samples. And up to about a little less than 20% of the samples are actually coming from this deterministic inclusion, although sometimes it's none. And we're showing you a problem where there's a lot of deterministic samples. Sometimes there's none, and that's fine. But I just want to stress that this can be up to 90% of the probability. And so if we were to miss any of these very important rows, it actually has an effect on the quality of the solution. And so that's why this hybrid deterministic sampling with random sampling can be a quite powerful tool that's not even specific to tensors. And then you might ask, well, how much does this deterministic sampling cost? So it does cost more. And so it's sort of a balance between accuracy of your solution and cost for the sample. But in our runs where we put this into a bigger system, even though the deterministic may be a little bit more expensive on some of the iterations, there's overall actually not very little difference between these two approaches. So the sampling time is the bottom part of these stacked bar charts. And so this is where we just do everything with random sampling according to leverage scores, no deterministic inclusion. And the sampling is here. The extracting from the tensor is the purple. That actually takes a lot of time to pull out the right-hand side. And then the solve is this light blue. And so the deterministic version, it just increases the sampling time by some amount. This is an extreme example where there's a lot of samples that are included deterministically. It takes more time to compute all those potential top probabilities, but it's not much added expense, and it's something that we can potentially control. So now let me show you just some examples. We'll start off with a smaller tensor where we can compute the exact fit. So we're going to run the standard method, which is shown in purple, and I'm plotting time versus the fit. So that's the proportion of the variance explained. So it's sort of like X minus the model divided by norm divided by the norm of the original data. Each line here is an individual run. We did 10 runs. Each dot is an iteration in that model, and it compute the fit there. The solid line is a medium of the interpolated runs. And then the other lines we're just showing the hybrid method to keep the method clean, the plot clean. So we're doing different numbers of sampled. So this is a combination of deterministic and random sampling between 2 to the 15th and 2 to the 17th samples. Each dot here is one epoch. So an epoch is 5 iterations before we check the fit. So because it's a randomized method, you really don't want to check the fit every single iteration. And you can see it also goes up and down. That's one of the things that happens with these randomized methods. It's not always monotonically increasing, which is a disadvantage compared to the standard method. But we can see that it gets into the neighborhood of the correct answer very fast. We're really zoomed in on this y-axis. I also want to stress. And so the red gets, which is the lowest number of samples, 2 to the 15th, gets close, but not quite as good as standard. But the blue gets as good as the standard, and it does it more quickly for this small tensor, which is a 4-way tensor, 183 by 24 by 1100 by 1700 with 3 million non-zeros. The hybrid method with 2 to the 17 samples actually gets a better score. It takes a little longer. Now, because this tensor is small, you don't really see the full advantages. This is sort of our debugging tensor. I think it's the best way to show it. Now let's go to some of the bigger tensors, which is really our target. So the Amazon tensor is a tensor that's also available in Frost. It's about 4.8 million by 1.8 million by 1.8 million with 1.7 billion non-zeros. We computed a rank 25 decomposition, and we compare the standard method in purple as before, and the hybrid method with 2 to the 16th and 2 to the 17th samples. And notice that's about the same as it was for Uber. It doesn't really depend on the number of rows. And the best fit that we get with the standard method is about 33%. And it takes 7.5 hours per run on a dedicated computational node on our data science cluster. And compare that to these hybrid random sampling methods where we get the fits are comparable, 0.3380, 0.3397, so it's even better than the standard method. And then we are talking about 43 to 47 minutes, so up to 10x faster solution using these random sampling methods. And then the Reddit tensor is our big goal. This is the one we showed you in the beginning, just to give you a sense of how much effort it was to get those results that we showed you. That has the 4.6 billion non-zeros. It's 106 gigabytes to store this tensor. The standard method took 96 hours to run. It achieved a fit of about 5%. So we could increase that fit by increasing the rank, but the standard method gets a fit of about 5%. And then the randomized method, which is 2 to the 17 samples per iteration, gets a fit of that's almost as good as this one, and it only takes 8 hours to run. So it's 12 times faster. This is a big difference. I just want to note there's 10 runs, I think, here, 96 hours per run. That's a lot of runs just to get the standard method. But even this is still 8 hours, these randomized methods. But it's a big difference in our ability to do computations on these. So we've sort of shown you that random sampling can be a powerful tool to speed things up. We just posted the paper on arXiv. It appeared late yesterday. So here's the number if you want to look it up. So, how do you make CP tensor decomposition faster for large scale sparse tensors? We want to use matrix sketching. We've ran into various problems because we're sampling probabilistically. Things with high probability are sampled over and over and over again, and we want to try to avoid sort of wasted samples that occur when that happens. So we can either combine rows that are sampled over and over again, or deterministically include them, and we actually combine both in our experiments. Of course, you have to be able to sample efficiently. You can't compute all those probabilities, so you can leverage the KRP structure to sample independently from the different factor matrices to build up your sampled KRP. You also have to be careful about extracting data from your right-hand side, which is still our most expensive steps. There's probably more that can, well, I hope there's more that can be done there to speed that up. So we pre-compute the linear indices to extract those tensor fibers. And the overall result for these large-scale tensors is more than an order of magnitude speed up. That said, there's still many open problems, both theoretical and practical, in terms of picking the number of samples, and maybe they want to be different for each mode, how to pick where our cutoff is for including some samples deterministically. Robust stopping conditions, you actually are not guaranteed that the fit is improving every iteration because of the randomized least squares problems. We can actually, there are other methods that sample based on both not only the KRP metrics, but also the right-hand side. And we can also look at parallelization of the method and many other things. So I want to thank you for attention. I give our email addresses if you have questions, and I'll open it up for questions from the group.
Okay, thank you very much, Tammy. Very rich talk, many things to think about actually, and impressive results experimentally. So at the moment, there are no questions in the question and answer, but I do have a question on something very basic, I would say. So the whole process still relies on alternating least squares.
Yes.
And this is really bottleneck. So any idea how to go around this? Do you know of any alternative?
Yeah, so it's another future work is how to, I think we can use related ideas to speed up the gradient computation that can be used in direct optimization approaches and like stochastic gradient descent.
Okay, I see. So there are two questions just came up. One is by Osman Azif Malik, would it be possible to use sampling without replacement to avoid sampling high probability rows multiple times?
Okay, so I'm smiling, and I don't know if you can see Brett. He's smiling really big. We had hoped that that was possible. And Brett, do you want to comment on this, or?
Sure, I can make 2 comments about the difficulties. So the primary reason that it's hard to do is that calculating the probability of something being included with sampling without replacement just is theoretically and computational time. It's just a lot of work that prevents you from you need that probability to be able to make the estimator unbiased. And so that's the main bottleneck, is what is the actual probability of choosing that sample when sampling without replacement. But the other thing is this this hybrid sampling ends up being nicer because when you sample without replacement, you end up having to keep checking your samples over and over again to make sure you get that a unique sample overall. So I think computationally, it actually ends up being a much nicer procedure to end up just doing rejection sampling on your deterministic samples.
Okay, thank you. One more question from Dario Fazzino, who asks, what about other tensor formats such as tensor train?
Yeah, so what we're doing, I don't know, I don't believe that has any direct application to tensor train. I haven't really thought about it, but I will say that it seems that all the methods that are applying tensor train to any sort of, you know, an actual data tensor versus maybe sort of a functional form have to use some sort of randomization, like cross approximation is maybe the main method, and that can be interpreted as a randomized, well, it is a randomized approach. And so I think that's the only hope for getting good tensor train approximations in a reasonable amount of time, if the time to compute your compressed version it matters.
Okay, so one more question from Volker Merman. What would happen if your data come from problems arising from PDEs? Can the same ideas be used?
Let's see. Hopefully I can ask a question back. So in what does the tensor look like in that case? Is it?
Well, I guess in different,
thinking of functional form
directions, X, Y, and Z, say, would have different tensor direction modes. But that I didn't ask the question, so I don't know whether Volker is the same.
Yeah, I don't know. I don't know because I don't quite understand the question, but maybe Volker and I can email offline. And the main thing I would say is that the randomized methods hold a heck of a lot of promise. There's a bit of a learning curve to start using them. And I think every problem needs a fresh look at what's out there. But they're extremely, extremely powerful in terms of breaking curses of dimensionality.
Okay, so I'll pass it to Jörg for the YouTube chat.
Okay, so
Daniel
takes care of the YouTube chat today. So there are quite a few questions on YouTube. Let's start by following up on a question by Valeria. So Alexander Litvinenko is asking, how do you feel about ALS, about its limitations? Is there a problem that it may end up with quasi-optimal solutions?
Okay, so how do I feel about ALS in general? ALS is still remains hard to beat. And any of the methods could end up with quasi-optimal solutions. So I don't know that ALS is necessarily better or worse in that case. The main place is sometimes you want to use direct optimization as opposed to alternating these squares when the number of modes, the number of dimensions is, the order of the tensor is higher. Sometimes there seems to be some advantage to direct optimization. And then as I said, we hope that some of these randomized methods can be applied in that context as well to compute the gradient. And I've also in other work have done some stochastic gradient work in those situations. So I think there's also hope for randomization there.
Okay, thanks. And then there are quite a few questions on sampling. So the first question is, can you say anything about the conditioning of Z? The typical conditioning of Z, is it relevant? And can you say something about it?
So do you mean
the matrix Z, which you have, for example, on slides 21?
Oh, okay.
And follow.
So, Brett, I saw you nodding. I didn't know if you wanted to jump in.
Well, I'm not. The one thing I'd say is that I think they might be getting at conditioning for the least squares problem, but I think the important thing, at least for us, is more this leverage score structure of the matrix Z. I don't know if Tammy has more comments about, but like the main thing is that we spent a lot of time thinking about is what do the leverage scores of a Khatri-Rao product look like? And one of the things that happens is because of the structure of that bound, they actually kind of become more concentrated. The coherence kind of goes up when you take the Khatri-Rao product of a bunch of matrices. And so more than anything, that was the most important thing about the matrix D for us.
Mm-hmm. Okay, thanks. Then there's a question by Martin Stoll on using DIME and similar techniques, so column selection techniques in general, deterministic column selection techniques. So how do you see their role in the context of your work?
What was the method that?
So DIME is a discrete empirical interpolation method. It's you can view it as a deterministic technique, a greedy technique to select columns.
Oh, okay. I don't know much about that, so I would be definitely interested to learn more.
Okay,
so I can't compare. Sorry. I will say for the previous one, Brett Bader and Gray Ballard did look at conditioning of Z at some point, but I don't think it quite matured enough to put anything out.
Okay, very good. Then there are two questions on the number of samples. The first question by Jörg Liesen on, so how did you choose 2 to the 17 samples for the Reddit tensor? How did you make this choice?
I'm going to pass that to Brett.
So most of the sample choices in these problems were made kind of numerically by kind of varying them and looking at like the quality that you got out. So that, as Tammy mentioned, that's one of, we think, an interesting open problem is, you know, being able to give a better answer to like how you choose the number of samples. I will say, surprisingly, across all the different sizes of tensors, 2 to the 17 actually worked pretty well from the Uber tensor to the Reddit tensor. It's about like 138,000 samples. We only had one tensor where we actually needed to increase that. And we think that a lot of those problems were in the case, you actually end up with a matrix where a lot of the residual is out of the column space of your matrix. And that was when we had to, you can see in the paper a few other techniques in increasing the samples that we use for that case.
Okay. And then I have a question by myself. So on this bounds, you have this typical epsilon to the -2, whereas if you look even on the cover slide here, on the conclusion slide, so it looks a little better. I mean, is epsilon to the -2 something which you observe, or does your method behave better in the pre-asymptotic phase at least?
Yeah, so the epsilon to the -2 is a little bit pessimistic in most cases from what we're observing. And yeah, what we're showing is the results that correspond to that epsilon. No,
No, so I was actually going to try and clarify that. So there's two things that you can actually calculate the difference between. One of them is the full residual for your sampled solution and your true solution. The epsilon in the guarantees is actually between what we'll call the sampled residual, which is where you calculate the residual in your sampled system with your solution, and the full residual for that same solution. And so it's actually more a measure of your estimator of the residual, and that's what the bound is for. But what we're showing is what's relevant for our least squares problem, which is how close is the residual of my sampled problem to the true residual.
Okay, thanks. Then there are two questions on hardware aspects. The first one by Click Moda, who asks, which kind of hardware did you use in your experiments? Any fancy stuff, I guess, he's asking for.
So all the experiments were done on a cluster at the lab. The main thing was that for the Reddit tensor, we actually needed to use nodes with like 1 terabyte of memory because you had to make multiple copies of the tensor. All the other ones were on 256 gigabytes. If you want more details on like the specific processors, they're actually just stated at the top of the numerical results in the paper.
And I should also mention we did everything in MATLAB. Yes. I forget that, like, I always do everything in MATLAB. And so I should say we did everything in MATLAB.
Oh, okay, we're all pleased to hear that. The final question is by Rich Woodhook, who is picking up on the parallelization you mentioned in the conclusion. So which parts do you think are particularly tricky to parallelize?
I'm going to say the data movement is going to be the worst because it's already the worst part.
Okay.
And Brett, did you have any different?
No, I was actually just going to use it as an opportunity to also mention we're also interested in kind of making like a distributed version. So it's actually really nice that, say you had distributed data in your tensor. You could basically sample on one node and then pull the fibers from a distributed tensor and solve it on the same on this specific node that contains the factor matrices. So then that involves, I think the tricky part there is, right, you then need to basically write some software to index and pull the fibers that you sample.
Okay, thanks. So these were all questions from my side. So I give the word back to Bart, I guess.
Okay, thanks Tammy and Brett for this very informative talk. Let me show you the slides of our next upcoming talks. Yes. Is this visible?
Yes.
Yes.
Okay. Okay, good. So you can see we have lined up quite a few interesting speakers for the next coming weeks. We also have a break in the middle of summer, so please tune back in September 9. Okay, I see it's a bit of a problem with the sharing. I hope to see you again next week for Laura Gigori. Have a nice day and bye.